Okay, welcome to the very first lecture of Advanced Applied Econometrics this semester. I mentioned that already. This week we will go through the statistic review with some important probability, statistic theory and concept that will help us to proceed further with the econometric material later on. And even though it's sort of a comfort for me to realize that you have had quite a careful review of this concept back in the winter term during the quantitative method of empirical research module already. Here we will still go quickly to all the concept, if not deep, and you still have the opportunity to ask the question when something is, for example, too fast for you. And that's the reason why I decided not to structure the slide in order to adapt to the change in the quantitative method class. So we will go through the concept of discrete and continuous random variables, expectation and moment, and then we look at multivariate distribution and conditional distributions. And these concepts draw from the appendix of VPIC, which I will also upload the scan on eCampus shortly after this, and talk quickly also about sampling distribution. What is it and why is it so important? So let's go. Before we go into the content, I would like to make some recommendations for you in case it's easier for you, like it used to be for me, to have some visualization of the concept, the theories that we're learning here. So there are the two websites that I found during some part of my learning progress that I found very fantastic. Now, let's look at it quickly. The first one is called Seeing Theory. So there's a very nice visualization, not only that the theory, the important concept in probability and statistics is visualized, but you can also interact with the visualization here. So they have quite a lot of concepts that we go into the slide today, which created by a group of students in the university, the Brown University in the US. Now, here, for example, you can see what is the chance event, what happens when you toss a coin, when you roll the dice and roll the die 100 times, a lot of things that you can manipulate and interact here in order to help you to have a clearer view of the theory. The second website is the Sentosa. So you see again, there's a lot of visualizations, also interactive, and you may also find not just about conditional probabilities. For example, that's an important concept. Central limit theorems is another important theorem in probability, but also all sort of other puzzle or quiz and explain real life phenomena. So they could be fun. So check it out. Okay, now let's go really into the material. The first thing is the discrete random variables. But before talking about discrete random variables, let's talk about random variables itself. What is that? So in general, a random variable is something that can take different outcomes depending on the state of nature. Putting it differently, when there is uncertainty about which outcome or which event will occur when you think about a variable, or the probability of any specific outcome is smaller than 1. For example, which question will appear in the exam or in your in-class test, or which block types you have, such things. There's always uncertainty, and it's called random variable. Okay. And now come to the question about the discrete random variables. So discrete random variables are those random variables that the possible outcomes, the set of possible outcomes limited. For example, you throw in the dice. If the dice fair, you know that there's 6 different possible outcomes with equal probability, right? Or you toss a coin, or like I said, your block type. These examples seems to be that the number of the outcomes relatively small. Now, however, you have to keep in mind that even when the set of the possible outcomes is very large, for example, something with 1,000 different possibilities of outcome. Now, however, when you know exactly each of these 1,000 outcomes, and there is no 1,001 observation, then is still the discrete random variable. Now let's look a bit at the notation. So for example, here is the probability for the dice experiment. For throwing a dice is a random variable now. So the probability of each outcomes is equal 1/6. So at the end, all the probabilities of these possible outcomes sum up to 1, right? That you know already. So usually the random variables, example, throwing the dice, is denoted by a capital letter, here Y, the capital Y, and a specific possible outcome, for example, 2 or 3 or something like that, is denoted by a small letter. Here, the small y. That's the first thing to pay attention about the notation. Secondly, as we based our course content on VBAC mainly, so we make the consistent notation of probability, or here, for example, let me jump ahead to expectation with the curly bracket. However, in other textbook, in other materials, you will also see the normal brackets like this, or the square bracket like this. So they all valid. There's nothing bad about preferring one to the other. Okay, but just here we use the curly bracket. Keep that in mind. Now, here is for the dice, and let's generalize it to a general case of a discrete random variables. We will have something called the probability mass function now to characterize the probability that each event or a specific event or outcome occurred. So here can be denoted as small fy equals p for probability that the outcome of the random variable equals a certain possible outcome, small y, and all the probabilities sum up to 1. Easy, right? We also have the concept of expected value, which I will talk more in the next slides, and denoted as E, the capital E with curly brackets of the random variables inside. And in the discrete case, it just simply means the weighted average of all possible outcomes, with the weight being the probability. What possible means? It means that you may not observe it when you do the experiment or you draw the sample yourself, but you know that as you keep repeating the experiments or as events continue occurring, there will be the chance that those outcomes will occur. Now, okay, so here is one example, pretty simple to start with working in R now. But before that, as I said, because you had the review of this concept just last semester, so for now we skip the first task. This one is pretty trivial. If you can't remember, then please go back to the slide of that part in the quantitative method class, okay? And then I will also skip this part, as you probably know that right now, but for now, just remind ourselves quickly that the expected value of the dice random variables is 3.5, right? You weighted outcome by the probability, with the probability being, sorry, 1/6, right? For each possible outcome, each of 6 possible outcomes, right? Okay. The third one generate 10 outcomes of the random variable and calculate the sample mean. I would encourage you to try it at home if you have a dice yourself, okay? So we don't do that here. And now let's focus on what's going on in R if we put that experiment in there. So let's go. Okay, so here is the R file, the R script that we used for this introduction lecture. The first thing I always do when I open an R file is to run this command. Why is that so? Before that, I have some certain object here, which probably I had that from earlier use of R. And then make sure that I clean out those objects and don't mess it up with what I want to do now. Okay, so the experiment we want to draw the sample here is about throwing the dice n times. Let's say we want to throw it 1,000 times. So now I will assign a variables n equals 1,000. Why do I have to do it here? Why can't I just put simply, for example, 1,000 here? As a general principle of programming, you should try to make it as generic as possible, so that it's easier for you later when you want to edit something. Because if you have 1,000 and every time you use this number you have to type 1,000, then there will be the time that, for example, you want to increase it to 10,000. You have to go back every place that you have that number and change it. If you miss one, then your analysis mess up. Okay, so now let's make a random variable called dice, simply the dice. And with this command, we create a sample for this random variable. So the dice is exactly the sample of that random variable. Throw in the dice, not the random variable itself. Okay, so what does that mean? Sample here is a routine, or you can call it a function, a built-in function where you can draw a sample of random numbers from 1 to 6. So it could be any of these random numbers, integer. So we don't talk about decimal numbers yet. And you draw the sample size of n observations and possible outcomes, right? Among 1 to 6. Replace equals true, which means with replacement. Now, it should be, because if you don't draw it with replacement or without replacement, it means and every time one of these 6 integers occurred in your sample, the program will throw it out. So after 6 times of occurrence or after several times, then you don't have numbers to draw or observation to draw anymore. So imagine you draw one paper out or you throw the dice, and then you throw the next one, 6 faces of the dice still there, right? It's not gone. So that means replacing. Okay, so let's run this. The way we run is putting the pointer on the sample line and press Control Enter, right? You must know that, and then it automatically jump to the next line. So now by writing the object, the R object along, if you press Control Enter, it will view in the console. So this part is the console, right? Okay, so that's how it look like for 1,000 numbers. Sorry, 1,000 observations can be any random number from 1 to 6. Okay, now let's count the frequency of this sample. So how many times each outcome, each of the 6 number occurs. Now, put the pointer there. Table is another command to count the frequency, right? And let's fill the frequency. So for example, the phase with only one dot occur 150 times, then 2 occurs for 177 times, and so until the number 6, right? We could also calculate the fraction, which is the ratio of the frequency of each outcome over the total size of the sample, right? So it's equal to frequency FEQ divided by N. And simple view the fraction, because we have the sample size is 1,000, so the fraction looks very analog to the frequency. But if you have something like 2,000, 5,000, then it will look different, right? Not so easy to relate. Okay, and then we could plot the frequency itself. You see here. I could also zoom it out, but let's just stay with it for now. So that is the frequency when we put it on graph, and you can see that it look pretty not precisely equal, but there's no big difference among the frequencies of those 6 numbers, right? And then we could also plot the fraction. The same thing. Okay. Okay, now we move on continuous random variables now. So contradicting to the discrete random variables, in this case, we have infinite number of possible outcomes, even within a very narrow interval between 0 and 1, or even I could even make it smaller, between 0 and 0.1, still infinite numbers of outcomes. If you cannot convince yourself that yet, it's also understandable. I mean, we know that these decimal numbers is there, but we rarely encounter it or see it, the difference in real life, right? Then let's take the number pi as an example, the famous pi. the constant. So usually we know it's something like 3.14, right? But it's not the end of the story, because you can go on with further decimal numbers behind that: 1, 5, 9, 2, 6, 5, 3, 5, 8, 9, 7, 9, 3, 2, 3, 8, 4, 6, 2, 6, 4, 3, 3, 8, 8, and I could go on forever like that, as up to hundreds of thousands of decimal numbers. And indeed, earlier time of the history of probability and statistic researcher have studied the randomness of thousands, the first thousands or the first several thousands of these decimal numbers of pi and other constant like the constant e as well. So you can find it in a book of Deborah Bennett, that I recommended. Nah. So it's really fascinating. Then, knowing that, we should accept that these random variables can have infinite number of different outcomes, even in a very small intervals. And because of this infinite possible outcomes, the specific probability of each outcome is 0, because you only have total probability of 1 for all outcomes, and divide by infinite number of outcomes, right? So each possible outcomes have probability of 0. Therefore, we could not write it before. Remember, in the discrete case, we have P large Y equals small y equals F, right? And now that's not possible anymore. That's not valid anymore. Instead, we could only calculate the probability of Y falling within a certain range between A and B. And here we have to use a special techniques. We cannot sum up anymore, but use integral. The scary notation of integrals here of the Fy when Y change from A to B. And when you integrate this function Fy over the entire range from negative infinity to positive infinity, then the total area is 1. So let me draw it a bit here quickly. Okay, let's say this is Fy, and we have a curve like this, the famous bell curve, right? And here's A, and here is, for example, B, right? So you can calculate the probability that your random variables, the outcome of your random variable occurs within this range between A and B as the area below this Fy curve from A to B. And the way to calculate that area is to take the integral. So that's the general idea. So what is Fy? It is the probability density function. The function that when you take the integral of it from A to B will give you the probability that the outcome of the variables fall between A and B. Okay, now we move on to the concept of cumulative density function, which is denoted usually as the CDF, as planned on your slide 6. Okay, so the cumulative density function usually denoted as the capital F of y. It means the probability that your random variables y, the capital Y, the random variables, takes a value smaller or equal to a certain point. Here, the small y. And it's the integrals of the probability density function as before denoted as the small f of the distribution from minus infinity up to the point small y. Graphically, it would look like this. T. So the distribution, let's say we have a distribution just like a famous bell curve, right? And here is a point y. And if you integrate to calculate the area below that, sorry, this should be PDF, up to the point y, then you have the Fy, which is the probability that random variable takes the value smaller or equal to y. So that's the idea of the cumulative density function now. So now imagine this value is y equal a, and then we have another, let's change the color, point B. So here we would have the area that I'm marking now with the pink color up to the point B under the PDF curve is the cumulative density of B. So let's write it down. Just like here, the area of what I shaded, that is the FA, right? And below there you have two areas actually. One area where the pink overlaps the blue, and the area with the pink alone is FB now. So one thing you could realize already is when A, no need for brackets here, smaller than B, then FA is smaller than FB, right? The area below the curve onto A is smaller than the area below the curve onto B. And this area, because area, right, must be larger than 0. However, because of the total probability of the whole distribution must be 1. Therefore, this cumulative density either of onto A or onto B must be smaller than 1 and or at most equal 1. So another thing on the slide is Fy must be between 0 and 1. Now, then how about now if you want to calculate the probability that the random variable fall between A, that's a Y, large Y, right, and B. How to calculate that? So the probability that Y falls between A and B, we showed previous slide already, which is the area under the curve between A and B, right? So to take the area, simply take FB minus FA, right? Then we could have equals, this is only the one marked with pink on the graph, right? The area between A and B below the PDF curve. So it actually equals this area, right? Entire area below the curve onto B minus the area onto A on B. No? Right? So therefore it follows directly in notation terms that it equals FB, let's write it not there, but here. So that's easy to say. FB minus FA, right? So the value of the cumulative density function at B minus the value of the cumulative density function at A. So that's what said in your slide 6. So now, what if you want to draw the CDF as a curve, not the area? This is CDF, it will look like this. So here is 0 now, and the further you go, let's say, the more it approach 1, because at the end, if you integrate the whole area below the curve up to positive infinitive, then it must be 1, right? And this is the value it takes for A, for example.